Hey, thank you, Davide, for this kind introduction, and thanks for inviting me over here. I hope you can see my screen. That's the only question. That everything's fine.
Perfectly fine. Yes.
Okay. Yeah. So when I saw this workshop, I was wondering what to actually talk about today, and what I'm going to talk about today is from HD maps to NO maps, or to basically no maps. So this is motivated by my work that I've been doing in the past with my group, and also at TRI, where we have basically been building self-driving and automated vehicles that can drive in an automated fashion. And the work that I'm going to present here is mostly the work done with my team in Freiburg, my group in Freiburg, and which actually sits in the building right behind me right now. Weather is beautiful here, sun is shining, and greetings from Freiburg. So it's basically my co-authors, or the people who did most of the work, are actually listed on the slide, and I apologize for everyone missing here. So what actually is the problem? So as we know, many companies in the automated driving space use so-called high-definition maps in order to actually build their automated driving capabilities. And these high-definition maps may have several purposes. They support perception, tracking, localization, prediction, planning, and control. So you can see a few of those high-definition maps that are being used on this slide. The bottom two ones are from Waymo, where you can basically see the ground, and also data associations where traffic lights are, which actually eases navigation through intersection. And the top video is an HD map that we are using at TRI for localization purposes, and many others as well. So they're great, and they help to build autonomous vehicles, but they are also problematic, and from various perspectives. And first of all, like, they are expensive to acquire, and also by building these maps, you make kind of like the implicit assumption that the features that are contained in the map are actually available. And on the video on the top, that has been recorded in Ann Arbor by my colleague Ryan Eustace, you see a typical winter scene, like when the snow melts, then basically the majority of features might disappear, and these maps might actually be completely useless for navigation. And in order to solve this problem, there's basically only one way in the very end, namely that we are going to be able to deal with changes in the environment. And if you extrapolate this to the very end, then we actually need to be able to infer these type of maps on the fly. And it's also basically a blocker for the level 5 achievement, because there in the end we cannot have, because of the expensiveness of these maps, we cannot actually build these maps in advance. We heard this in the session before. It's going to be impossible to build maps of every environment for robots. And the bottom image is actually also just a screenshot from a video sequence that I keep watching over the past month, which is from JJ Ricks, who is a guy who frequently orders Waymo cars and jumps into these Waymo cars and lets these and drives around with these Waymo cars and gets them into particularly difficult situations. And this is one of the picture of one of the latest videos where the car is basically stuck in the middle of the road simply because there's a few cones separating two lanes of this road. And he's stuck there for several minutes, and we're recording his video. I do not want to finger point here. On the contrary, I want to basically say, or want to invite you to look at these videos in order to see how far those people got with HD maps. But still, where the limitations are. And this is, for example, construction sites where the real world deviates from that what is in the map. And this is one of the key blockers there. And in this talk, I will talk a little bit about like change detection, which is an important and still open issue for when you are like restricted to HD maps. And then when you plan to give this up and basically say, hey, we do not want to use maps at all, then you basically, I mean, this is also not completely correct. Do not use maps at all, because everything that you accumulate over time, and even if it is just a short time window, it's going to be some sort of map. Even if you accumulate multiple perception into a consistent representation, this is not that wild thing that we do in SLAM, building these large consistent maps. But what we're basically doing there is accumulating information over time and in space in order to potentially more properly plan. But that requires a lot of semantics, tracking, inference of topology, something that the last one where we are particularly bad at this time. So the first one is a work that I've been done with colleagues from BMW, actually, with a PhD student who started a couple of years ago, and it has been presented at ICRA in live, actually. So the motivation is exactly that, what I mentioned before. HD maps are useful, but hard to maintain and super expensive to maintain. And whenever you have changes in the environment, and this is kind of like the dynamics that I'm speaking about here, is that you basically need to have the capability to react to this. And the idea there is not to do this with expensive mapping vehicles that every company has and remap the entire world every day, but rather use vehicles that are out there to detect that there are changes. And the question is how to basically do this in a cheap fashion with potentially cheap sensors. And to motivate this also here is a kind of like an image where you can see where the light is. And basically what you also see is that there's a lot of light along the major roads in the world, so which basically means that you can easily utilize the data from people driving through the world to actually detect changes in your maps. But you want to do this not with a super expensive vehicle. You basically want to do this with cheap sensors. And the cheap sensors that we typically see in vehicles, and basically utilizing the fleet or the crowd, is the vehicle position, odometry measurements. Then we have GPS measurements, and you might be able to extract lane marking observations and road edge observations. And both the latter two are basically contained in the map as well. So with this, you can basically like figure out changes in the lane markings or even the road edges. And the way we did this in this work was basically, first of all, tracking these features from live images. And as a highway close to Munich, Bavaria in Germany, you can actually see how the position of the vehicle and the features of the road are basically tracked while the vehicle is driving. And then what we then do is we use this information in a particle filter context to basically detect the innovation. And as you all know, this comes with a lot of noise. And what we do here is basically using boosting, ADA boost for the classification task. And in order to still deal with the uncertainty there, we bin the entire road network into 10-meter bins, and then throw the classification results for these corresponding bins into those bins and have a majority vote with a dynamically adjusted threshold in there. And the application, or the qualitative application of this, can be seen here. So basically on the right-hand side, what you see is the current yes/no votes that you have in that bin. The white circle determines the threshold that we're having. At the bottom circle is the ground truth. And you can see here where the vehicle slowly enters a construction site, at how the color changes from basically green to red. And here you on the left-hand side, so you see a larger construction area in the vicinity of Munich, and the projections of these estimates onto this. And once you have this, then you can basically potentially either use the fleet data itself to determine new features, or potentially go there with one of your expensive mapping vehicles to reconstruct or to relearn the map over there. There's also some quantitative results about how this multi-trace classification, or basically using the fleet, actually helps in that context. So this is one task that we need to solve. If we decide to go for maps and want to use these maps in dynamic environments, then we need to be able to, first of all, detect changes. And the second and even more harder part is then to potentially automatically rebuild them. And in the long run, if you decide, and if you go for this term and say basically HD maps is a lane technology, and you shouldn't use those, then the only chance you have is to basically learn them on the fly. And this is something that, like, if you want to do this, then you need to solve multiple tasks there. You basically need to infer the semantics. And then the extremely hard parts are also data association tasks, like tracking individual objects, associations of traffic lights. So is a particular traffic light relevant for the lane I'm currently in, is one of the really hard problems in this context. This is information that you typically find in these HD maps. And then you also want to talk about or learn about the topology of the road structure, and in particular, the intersection topology, which is an extremely hard problem. And as far as I know, there's very, very little work that actually deals with this particular problem. And I will talk a little bit about the few and steps or recent results we have towards these type of problems. The first one is like this work by Abhinav Valada's group, mostly about learning semantics and also the dynamics. And this is about panoptic segmentation and LiDAR-based panoptic segmentation. And for those of you who don't know exactly what this is, basically you want to infer what the environment looks like, what is the stuff around you, and not just deal with the point clouds, like as you see here. So what you typically have is on the left-hand side a point cloud, and then you want to know what is the stuff that you see, what is the class of every point in that point cloud. But then you lack basically the instances, and the instances are extremely important for tracking and prediction purposes. So you also want to do instance segmentation, and when you throw those two together, then you get that what is called panoptic segmentation. And this is one of the approaches that, or one of the techniques that you need basically for building truly autonomous vehicles. And this is the network that we have here. Like, you start basically with the scan unfolding projection, and then have this backbone over here with the encoder network, and then and then the feature pyramid network over here in a two-way one, and then the proximity convolution module and the range encoder network, and then that goes to the semantic head, where we basically do have an instance head also, and a panoptic fusion module at the end, perform panoptic prediction, and then have a k-nearest neighbor approach to map that back towards the LiDAR point cloud. And yeah, and here you can see a few qualitative results on the Kitty and new scenes data set. Again, quantitatively, we are outperforming the state of the art here, and by a quite substantial margin, as you can see. So here's a few examples about this in action, the panoptic segmentation. And the key question in the next step is basically to turn this into not only a segmentation or frame-based approach, but also go temporal, basically have these estimates over time. And that would mean that you not only perform panoptic segmentation, but you combine this with some sort of tracking mechanism to actually establish temporal consistency. And this is what is called multi-object panoptic tracking, or MOPT. And this is basically an extension of this approach. Find this in this paper over here. And the idea there is basically to combine semantic segmentation, instance segmentation, and object tracking to finally obtain multi-object panoptic tracking. And this is builds upon the efficient LiDAR-based panoptic segmentation architecture, but additionally has three heads basically for semantic segmentation, instance segmentation, and then multi-object tracking. And so there are two applications of this: a vision-based application where you only do this using vision data on the virtual Kitty 2 data set, or a LiDAR-based one version where we applied it to semantic Kitty. The data sets that we used, and then on both data sets we outperformed the state of the art at with the relatively same performance. So this is for the LiDAR-based one. So you can see here exactly with respect to the panoptic tracking quality, the highest score of this approach. Here's the application for the vision-based, method where it is not perfect, as you see, but it is also, at the same time, it is also a hard task. And so same color means same instance. And but it's always good to have something to do for the future. And here is an application to LiDAR-based panoptic tracking. So what you see there on the right-hand side is that these point clouds are actually consistent, like for the individual cars, which means that the system can consistently track the cars over time. Here you can also see this in a different projection. And now at an intersection where this tornado over here is basically another car moving around, and by the fact that these individual scans have the same color, it actually means that they are consistently tracked over time. So this is one of the techniques that you basically need when you want to go towards more autonomous driving and potentially in the end without any additional information. So basically enable these vehicles to do this without any prior information. Another challenge is making the perception and the semantic segmentation more robust. And again, we have this problem that we basically need to, in the end, if we perform this perception or solely rely on machine learning and perception, then we need to have capabilities to generalize across domains. And this is a paper that two of my students, Johan and Yannick, worked on, basically bridging the day-night domain gap in semantic segmentation with, in this case, thermal images. Right. So here's an example where you can see standard conventional semantic segmentation approaches applied to night imagery. And as you can see, the performance is by way not as we are used to it given daylight images. Right? So the question is, how can we actually extend this towards night vision? And here is an image that, or the short video clip that shows the performance of infrared images in a night scene. And from there, you can actually see that the domain gap between day and nighttime is not as big as for RGB. Right? In fact, there is also a domain gap because of the difference in temperatures and also the deltas in temperature differences at night, but it's not as big as for for RGB. And again, I mentioned this before that we are trying to utilize the thermal input to actually learn a better classifier also for RGB. And so how this works is basically that we are training the system on papillary data. We have that so-called teacher network that we then can actually utilize to train the HeatNet model that uses RGB and thermal. And we transfer this to the night domain by using a GAN approach. We're basically trained to mimic the output that we obtain with daylight imagery from night images. Right? So this is the trick over here. So that basically in the end, you get the similar segmentation results for night data that then we get for day data. And so this is a vehicle that we have been using that has a thermal camera over here and RGB cameras to record the data sets. These are the this data set is publicly available, so we can actually also utilize this data set day and night and thermal images. And we then generated also some outputs here on the left-hand side. The left two images are basically RGB and thermal input, and the right-hand side is the output of the RGB teacher. That is actually the network learned from papillary data. And what the output that is most interesting for us is that of HeatNet RGB thermal. That's basically the segmentation results that we get over here. Interestingly, we can also use the structure currently to train an RGB classifier on night images that performs similar to those results that we get with the thermal and RGB images. And that is what you see basically over here. And that means that in the end, we can even apply this approach in a vehicle that only has RGB and no thermal cameras. So here's a few experimental results just to give you some ideas about how the system performs in changing environments, also with different illumination conditions. But this is with terminal information being used. And the final, and very briefly, I want to talk about that. What interests me a lot also is basically inferring the topology of the lane graph, which is basically a key structure or key aspect of an HD map and information that vehicles actually need for robust navigation. This is brand new and just hot out of the press. The idea there is basically using a bird's eye view representation, and I guess Raquel will talk a little bit also about bird's eye view representations in her talk, and directly infer the lane topology out of these bird's eye view. And again, we are doing this with multimodal inputs, which is basically the intensity information. We also have direction information of the individual vehicles, and also semantic segmentation, and throw this into a so-called graph RCNN and get as output the directional lane graph. And without going into further details, I'll just jump to the results and show you some outputs that we get from these networks, or from this network, on the data set that we have been using. And as you can see, it is not perfect, but it is an important step towards that direction. It's pretty good on just roads. It's not as good as I had hoped for intersections, but this is something that we will look into more in the future. So to sum up, right, HD maps are super useful, but limiting also, because whenever the world changes and is dynamic, then we get into trouble. If we commit to HD maps, we need to have proper approaches for change detection and remapping. And if we want to get rid of them, we need to substantially extend our perception capabilities with respect to other agents, domain adaptation, topology inference. And this is where we need to throw the entire machine learning technology at, and that basically is a topic that we discussed before. And that is also on this slide, is this transition from models to learning that has briefly been covered in previous discussions. And I guess this will come up also in our panel at the very end. That's it. Thanks a lot. And thanks again for inviting me.